And hey, the first thing I want to do is just give you the breakdown on how the first midterm went, which basically I'm very happy with. Many people did extremely well. And let me share my screen with you so I can show you how well a lot of people did. And yep, so you should be seeing it right now. You can see the average on the exam was just about 82. I don't know what to make of median and modes. If you like statistics, they're there as well because Excel does those for you. High score was 97 and a half. Two people did that. And you can see the breakdown, how the exam went. Four people greater than 95, 7, 90 to 94, etc. What's interesting about this breakdown is, let's see, that's 11 people were greater than 90, so that's 11 A's, and looks like 13 people in the B range, and so that's 24 out of the 28 people that took the exam got either an A or a B. So in general, I would say I'm happy with that. Not a lot of C's and D's, obviously, and then a couple folks down weren't successful in the exam. All right. My one thought, there's a definition of insanity that people sometimes use, which I think often applies in academics. And that's if you're not happy with an outcome, but you're continuing to do the same thing over and over again, well, that is the definition of insanity. If you're doing the same thing over and over again and expecting a different result, you need to change something up. And I can tell you this, something I've experienced. If you'd love to have an A instead of the B plus that you've got, for example, what I would urge you to think about is what techniques that I'm trying to get you to do aren't you doing? And I see there's still a lot of people that while they will slap in units at the end, for example, they won't use units as a check to find a small mistake. Typically, the difference between that B plus and that A is finding your own mistakes. And so setting yourself up to succeed by putting checks in place like unit analysis, like another example might be doing a problem a slightly different way. If there are two ways to do it the other way and see if you get the same answer. Little things like that I admit take time, but on an exam that's take home that you have the entire day for, it is worth a second to do. Again, the difference between the B plus and the A is often right there. Okay, checking units, I can't say enough about it. It just helps. It causes you to think things through, make things, make connections. I was working in my modern physics class with students last Friday, and there was a problem where there was no equation. All they had to do was make the units come out to what the problem was asking. And so it's a technique in physics. All right, that's my pitch on the exams. Basically, great job. Anytime you can get 20, what did I say, 24 A's and B's. Is that what I out of 28? Yeah, that's a good day for this business. So keep it up. Those of you that are happy with what you're doing, you're getting that A, and that's consistent with your goals for the course. Then you're doing what you need to do, and keep right on charging. And of course, everything's in Canvas, so you can see how your first midterm factors in with your homework and your classwork and your labs and your reading quizzes. You can see how that all breaks down, and you can see where your grade is sitting right now. All right, we'll move on. Let's see, is there anything else I want to say about that? Oh yeah, there is homework. The word homework just popped into my mind. As I was checking over the weekend, only about 2 or 3 people have done the homework yet. There is no lab this week. What I'm thinking of doing in lab, in fact, what I am doing in lab, is it's completely optional, but I will be going over the exam problems for the first half hour, maybe 45 minutes of each of the lab periods. Okay, so I'll come into Dr. Kem's section on Wednesday and do the problems for anybody that wants to see the exam problems worked out. I would say if the projectile motion problem is an issue for you, okay, so if you lost some points on the projectile motion problem, go back and look at the problems we did as a worksheet. There was a day of worksheets on just projectile motion problems. I did a problem, and we split up into groups, and there were 2 other problems. I think the third of those problems, very similar to the exam problem on projectile motion. The difference is the numbers and maybe the setup of it, but it was still a horizontal initial velocity of a projectile coming off some height. And so very similar problem, just literally different numbers. And if you had any questions on that particular problem, look at that. The second problem that we worked out, the closest one was perhaps that problem with a baseball pitcher, where in that case the ball was accelerating over some distance, and you had to calculate the acceleration using constant acceleration, and then figure out what the force was from Newton's second law. Well, this problem was decelerating instead of accelerating, like that baseball pitcher problem. So that one in module 4, a very similar problem in terms of the steps you go through. And seeing patterns like that is what makes physics a successful venture for you, if you can see the similarity to other problems. Anyway, I'll go over those two on the lab period, and additionally the 15 short answer type problems that were in Mastering Physics. I'll be going over those one at a time as well. And like I said, should take about a half hour to 45 minutes. All right, so that's it for the exam. No lab this week, completely optional. If you're happy with your grade, you figured out what your mistakes were, no need to come. But if you do have some questions, that's the time. I also more than willing to entertain office hours today at 9:30 and 10:30. I'm available both those slots for as long as it takes. And then same thing on Wednesday as well, 9:30 and 10:30 again on Wednesday. Now I'm not going to be able to do the Wednesday office hours. I actually have a dentist appointment, so we'll make another. If somebody needs office hours on Wednesday, I'll have to move it into the afternoon. Okay, after I'm done going over the exam problems with the Wednesday lab people. All right, moving on. We're talking about friction today. Any questions on friction before I get started? I'm going to keep sharing it. Here is the bottom line. We've been dealing with friction since chapter 4. It was one of the forces in our so-called catalog of forces, right? It was a force. The new wrinkle in chapter 5 here today is that you can actually figure out how to calculate friction, right? That's the deal here. Somebody have a question? I heard somebody maybe saying something. Okay, well, there's still two types of friction, okay? But now we know that we can calculate either the static or the kinetic friction once we figure out the normal force, okay? And in the two examples I'm showing here, the normal force is exactly equal to the weight. Don't count on that to be true, right? We've done multiple problems like on an inclined plane where the normal force is not equal to the weight, right? Made a big deal out of that in one of the pre-lecture videos. I think it was last week. They all start running together for me. Okay, if there's a cord, a tension that's pulling upwards at any angle, we did one where the cord was pulling completely straight up on the worksheets last week. And of course, that changes the normal force as well. But in all cases, the normal force is found from the vertical component of forces. And very often the vertical component, the y component of forces, add to 0 because there's no motion in the y direction in many cases. And so in this particular problem, we're showing, in these particular examples, we're showing that the normal force is exactly equal to the weight. And so then from that, you can figure out what the friction force is. If it's not exactly equal to the weight, you got to figure out what exactly the normal force is. Okay, so the problem immediately becomes two parts then. Figure out what the normal force is, and then multiply by a coefficient. And there's two types. There's a static coefficient of friction and a kinetic coefficient of friction. Those symbols there are Greek mu's, mu, which is, quite frankly, if you're trying to draw it, it's an upside down H, right? That's all it is, okay? And we subscripted S for static and K for kinetic. Static is when the object is in equilibrium, the special case of equilibrium, when it's at rest. Okay, that's static friction. And the thing you notice about static friction is it's a maximum. It doesn't have to be that big. It can be that big. Friction and drag, which is the other thing we're talking about today, will never cause motion in and of themselves. All they can do is oppose motion. And so that's why static friction has a maximum. It can only be up to a particular value. And the value it comes up to is that force value in newtons, which will counteract the sum of all the other forces in a problem. So in this case, the lady there is pushing on the object. The friction force will be exactly as big as it needs to be to keep the object at rest. That's how big static friction can be. If the maximum amount of friction that could be calculated from the normal force and the coefficient is 50 newtons, but she's only pushing at, say, 20 newtons, well, the friction force will only be 20 newtons. It won't go up to its maximum value if it doesn't need to be. We say that friction, static friction, and drag are constraint forces, okay? Dynamic friction is a constraint force again as well. It can't cause motion, it can simply constrain motion, okay? Any questions on that? Great. And so then I'll go talk real quick about kinetic friction. Okay. Kinetic friction is a constant value. Okay. It is simply the normal force times the kinetic friction coefficient, and it will be a value. It will just be another force that you have to add up as you're summing forces in the horizontal and the vertical direction. And you can see in this case, it could be an equilibrium problem if the force that the lady is pushing is exactly equal to the kinetic friction. Well, then she'll get the thing, once the thing is moving, once the box here is moving, it'll move at a constant speed in equilibrium, dynamic equilibrium. Or if the push that she's applying is greater than the kinetic friction force, well, it'll accelerate. The speed will continue to increase over time. And that's how kinetic friction works. It's actually a little easier to consider because it is just a number and you add it into the sum of the forces as we've been doing. All right, so here's my first poll question now. Let me open up polls, find the right one because I'm finally getting better at this, I guess, maybe a little bit. And we'll launch this poll and see what you can see here in this problem is you've got a 100 Newton object. I could have given you the mass and made you multiply by G yourself. By the way, G, for many calculations, you can just make it 10, right? 9.8 is close enough to 10. So this is about a 10 kilogram block here, and G is about 10, and that's where the 100 Newton comes from. And you can see that, I guess the question is, will the block move? So figure out what the normal force must be. This one's pretty straightforward. Figure out what the friction forces could be for static and kinetic friction, and then see if the block is going to move. Okay, about half the people are in right now. Give you all a second to do the math in your head. Hopefully you don't need a calculator for any of these. 26, two more. We lost somebody. We had 29, we went down to 28. Somebody's internet connection must be wonky, I guess, this morning. There, everybody's in. All right, I'll share the results with you. And you can see the majority of people think no. And I have to agree. Because look, here's the deal. If you calculate the two friction forces, you'll see that static friction is 40 newtons, right? 0.4 times 100, because the normal force is the weight in this problem, 40 newtons. And the kinetic friction is 20 newtons. And this is typical. The static friction force is often greater than the kinetic friction force. If you look at the coefficients in the table I showed you in the pre-lecture video last night, or go to your textbook if you want to see it real quick, it's very typical. In fact, I've never ran across a case where it was otherwise. The static friction force is greater. And, we sometimes talk about a breakaway force. You have to get greater than 40 newtons with that applied force in order to make the box move. But then once you break away and the thing is actually moving, the friction force drops from 40 newtons down to 20 newtons, doesn't it? And then continues to move, and in this case would accelerate due to a 10 Newton net force to the right. Okay, and so that's how you have to finish this. So definitely no, because the static friction force is the first force. It can be up to 40 newtons, and we'll talk about what it will be here in just a second. And so let's move on to there's my answer. And let's move on to the next one. And it's all the way down at the bottom here. All right, and let's launch it. It always moves to cover the middle of my screen. So now we got the 100 Newton box. It's pulled by a 30 Newton horizontal force. How big is the friction force? And couple people I see are going in a particular direction. I didn't ask how big the friction force could be. I asked how big it was. How big is the friction force? And so that's a hint here. I think you can change your answer if that comment causes you to reconsider. Not how big it could be, not its maximum value. How big is it in this problem? 26, a lot of opinions here. The majority is right, but I'm going to have to, I got 28, one more. Give you a second here. All right, not going to wait. So I'll share the results with you. A lot of people took the answer 40 newtons, okay, 9 people. And okay, so you can see right here, the friction force, well, the friction force, why am I doing that? I don't need the coefficient anymore. The static friction force could be 40 newtons, right? And that's why we have the words max right here. It could be up to 40 newtons. The kinetic force, well, it's 20 newtons. Okay, but we're only applying 30 newtons. So if there was a static friction force here of 40 newtons, what would be the net force on the box? The answer would be 10 newtons to the left, wouldn't it? And so would you be saying then that the box would accelerate to the left due to the friction force? And hopefully you realize that's not what happens, okay? In fact, I've seen other textbooks I've used where it's the static friction force is expressed as an inequality. The friction force can be as big as 40 newtons, but it'll very often be less than that. It could be equal, but it's often going to be less. And so in this case, the static friction force will only be 30 newtons to cause the sum of the forces to be equal to 0. Okay. The fact that the kinetic friction force is 20 newtons doesn't come into play until the block is actually moving. And then that's where that happens. So it's not 20 either. So 30 newtons, that's the answer. And think about what the ramifications for the 9 people that went with 40, what that would mean. Okay. And that's part of the checking your answer and thinking about, now, does that make sense once you've arrived at a conclusion, once you've done a calculation in a physics problem? Check to see that it makes sense. Okay. Because if there was 40 newtons pulling to the left, which is what friction would have to do here, you would have a net force, and friction would be the cause of motion. That is absolutely not what happens in nature. All right, questions on that? It's kind of an important point. So if that's not clear to you,
I
now's the
have a
time.
question.
Yeah, go ahead.
Can you explain again why it's 30 newtons and not 20? Because isn't the box moving?
No, it's being pulled, but it won't start to move until the applied force is greater than 40 newtons. Okay, let me go back to a slide that was in the video last night. Let me find it. There's the one I'm looking for. Okay, and so you can see in this particular case, the applied force is 30 newtons. And so the friction force is 30 newtons, keeping the block at rest. And it isn't, now in our problem, the maximum value is 40 newtons right there. Once the block is got 40 newtons or more applied to it, then it'll start to move, and then kinetic friction takes over. Okay, but you have to get the block moving initially. And in this case, since the applied force is less than the maximum static friction force, it won't move. And that's what's meant by this little glitch right here, even though it's happening at 50 as opposed to 40 in our problem. Okay, all of this range, the block is at rest. It isn't until you exceed the maximum value with your applied force that the block actually starts moving, and then kinetic friction comes into play. Make sense? Even if it doesn't, that's how it works. I can tell you this: if you've ever tried to, this happens often when we're trying to unscrew something. So we put the screwdriver on the head of the screw, And to get it to break free initially takes an awful lot of effort. But then once you get it moving, it takes less effort to keep it moving, right? And there's other reasons for that too. It's how tightly squished together the screw is to the top of the thing it's holding in place. But we can't talk about a breakaway, in that case, torque, in this case, a breakaway force. And so what has to happen before the block will move is you have to exceed the maximum value of the static friction with your applied force. And that's often hard to do. But then once you do free down, then the force you have to apply gets much less. Okay, it would only be 20 newtons in this case. We'll keep pushing on this point because it is an important one, and it's maybe not obvious, and it's the new thing I guess about friction here. All right, so there's the next question I'm going to do. We'll stop sharing that. We'll move on to 3, and we'll continue pushing. It's really the same idea over and over and over again, just to make sure you got it. Okay. And so now I've got this breakaway, this nudging force somehow has to get the block to start moving. And how big does that force have to be in order to get the block moving? Still got 30 newtons pulling to the right. How big would an additional nudging force have to be? Maybe it's a normal force. Somebody's hand comes and pushes on the block just a little bit, in addition to maybe a tension in a cable of 30 newtons. And I think most people see it here. Yeah, you got the idea. All right, 25 people are in. 26. All right, we're going to end it here. So I think we've said this, and most of you have it. The question I guess I don't want to answer is, what about 10 newtons? What if that nudging force was exactly 10 newtons? And it could go either way if it was exactly 10 newtons, right? But I know for a fact, if it's 9 newtons, there would only be a net force of 39 newtons to the right. And the friction force can be as big as 40 newtons to the left. And so the block won't move. At 10, it's kind of a coin toss. I don't know what would happen at exactly 10 newtons. I don't want to talk about that. But I know at 11 newtons, I'll have 41 newtons to the right, and the friction force can only be as big as 40 newtons. At that instant, the block will start to move. 40.00001 to the right, and the block is moving. Okay. And so then immediately, static friction goes away, and all of a sudden, you got kinetic friction. And that would be different. All right, questions? That's the way it works, I guess. And so let's move on to the next one and slide to the next guy here. And so in this case, the nudge force is removed and the block is still moving now. Okay, block is still moving. We're in a sequence here. We've given it that 11 Newton nudge to the right, got the block moving. And so now what is the friction force on the block? All right, looks like we got it. The majority do anyway. All right, 24 people in. 26, and I'm going to cut it off right there because most of you have it here. We'll share the results with you, and you can see that the majority of people say 20 newtons, and you're absolutely right. Once the block starts moving, you've broken away to make it start to move. Immediately, static friction is out of the problem, and we've got kinetic friction. And of course, 100 newtons times 0.2 is 20 newtons. The static friction force, once it's moving, 20 newtons. No greater than, less than sign, anything like that. It is, once it's moving, 20 20 newtons. And so that's exactly the right answer. All right, one more of these. Stop sharing, and we'll go to the very last one. And kind of here's the big deal question, I guess. So now it's moving. Hopefully this is going to say, what's the net force on the block now? Come on. There we go. So in your mind's eye, I guess you got to draw a free body diagram. Friction's that way. And it's kinetic friction because the block is moving, still moving. All right, most people see it here. "24 people in, 25, 26, that may up. Somebody's back. Excellent. 27. All right, we'll cut it off right there after a minute. And yeah, exactly what you'd think here. Once the block is moving, this is equal to 20 newtons here, because that's what the kinetic friction force is when the block's moving. And you can see the sum of the forces in the x direction is equal to the 30 newtons. I'll call that a tension. I don't know, whatever it is. 30 newtons to the right minus the friction force of 20 newtons to the left. And that's why I made it negative. And so that's equal to 10 newtons. And, it doesn't, I'm not asking in this problem, but I could have gone one step further. I could have said, okay, what's the acceleration of this block? Because I could have set the net force here, the sum of the forces, equal to the mass times the acceleration. Well, you would have had to take that and realize that if the weight is 10 newtons, the mass is just about equal to 10 kilograms. Okay, and so that would tell me that the acceleration of this block is equal to 10 newtons divided by the mass, which is 10 kilograms. And so I have an acceleration of 1 meter per second squared to the right. Okay, and that's what would happen in this problem if it worked exactly like I said. Initially at rest, because the 30 Newton force doesn't exceed the static friction force. If I give the thing a little nudge, an additional force of 11 newtons to get it moving, well, then all of a sudden the friction force drops down to 20 newtons. And then I have a net force to the right of 10 newtons, and the block accelerates off to the right. Questions on that? Okay, that's how it works. Nature has decided this. All physicists and natural philosophers over the generations have done is come up with what we call an empirical law to describe what is happening, okay, and why it's happening. It's nothing in the law explains why it happens. That's between nature and the objects, I guess. There is one point I should make, though, before we go on to do some problems, and that is, why is the static and the kinetic friction force related to the normal force? Because in everything we've talked about so far, the friction force is horizontal and the normal force is vertical. And generally we say we can completely decouple vertical forces from horizontal forces, but friction is the one coupling between the two. You have to solve the y component forces to get the normal force in order to get the x component force of friction, don't you? And if you watched how I did the problem on the video last night, that's exactly what we had to do. And so why is that? Well, if you just kind of think about your fingers, and I'm going to stop sharing this so you can see my hands here. Okay, so let's say I've got my fingers and my knuckles are approximating kind of the roughness of the surface of an object and the surface it's sitting on. Hopefully you can see the greater I push my knuckles together, the harder it would be to slide them by each other, right? And that's why friction is related to the normal force. Although surfaces that we look at appear smooth, a lot of them on a microscopic level are extremely rough. And so much like my knuckles, the more you push them together, the harder it is then to slide by. And of course, uh, a lot of work has gone into making materials like Teflon that even, not only look smooth on a macroscopic level, but when you get really close to it, apparently is smooth as well. And so things are very slippery on Teflon surfaces. Ice is another example. I think the reason is because any porosity or pitting in the surface of the ice often gets filled in with a layer of water, which is very smooth. And it's the water sitting on top of the ice which makes it so slippery and reduces the coefficient of friction. But if you push with a great enough normal force, even on slippery surfaces like Teflon and ice, you will get friction forces. In our course, being an introductory course, we'll often say, hey, ice, that's frictionless. Okay, but in reality, there always is a little friction. Our air track that you saw in the incline plane lab, we said it was frictionless because the cart was falling along on the cart, on the track, on a layer of air. But there's still, even with air, is a bit of friction that's happening. And most of you, I think, found in that lab, and I guess I'll know this week when I grade it, that the predicted acceleration was actually a little greater than what you measured. And the answer for why that is because even though we say it's a frictionless surface, there probably is a little bit of friction that slowed down the cart over what you predicted as it moved down the track. All right, here's what we're going to do next. I'm going to go over to and we got about 20 minutes, so we're going to break up into the breakout groups. If you look at the worksheet for today, which I'll share with you now, if I could, Acrobat, there we go. Okay, if you look, I give you some words like I always do, again, stolen from Senator Mikulski's nephew, who I used to work with. And is a block sliding down an inclined plane for group one, and another where the block is being pulled with a tension force. I picked these two problems because in both cases, the normal force is not simply equal to the weight. And so half the group's going to do one, half the group's going to do another. And then what I haven't talked about much today is drag. Okay. And there'll be two drag problems. Okay. And in both cases, you can assume quadratic drag. And I know this looks complicated, but I would tell you, don't worry too much about these coefficients other than what their units are. You just multiply them together. We'll always have to give them to you, or we'll give you everything but one of the coefficients. In general, we assume quadratic drag, although linear drag is so much easier to handle mathematically. Okay, but all the 1/2, this coefficient of drag, the density, the air, those are all just constants. In a lot of people's mind, they just lump them into one constant, often call it B of all things, lowercase b. All right, so drag is proportional to the speed squared, and the constant of proportionality is all those things, which just become a number when we give you all the values. For example, air, the density is 1.2 kilogram per meter cubed. That area there is the cross-sectional area of whatever is moving through the air, that sort of thing. Okay, so again, group one will do problem one here, just checking the dimensions to see what the dimensions of that coefficient C is. And group two will do a skydiver problem. And so at the end of the period today or before next class, you're either turning in the two problem ones or the two problem twos. And so let me stop sharing that with you and break up into groups here. And here are the groups doing problem one. I want 8 groups. Okay, create breakup groups. Doing one is Allison Buckwalter, Katie Eckhoff, Sean Curry, Tommy Hance. That's group one. Andrea Peterson, Chen Yi Lu, Kyle Waldorf, and Shanice Frazier. You're in group two. Anna Gantz, Ellen Daly, Emma McTurk, and Jahil. You guys are in group three. And in group four, Kristen Quillen, Jackie Cruz, Nina D'Addario, and Stephanie Provine. And so you guys are group one. Everybody else is group two, doing the two problem twos. Any questions? I'll jump around and help whenever I can. We'll see you back here probably in about 10, maybe 12 minutes or so. So get started on these.
Oh, hi.
Hey, Nina, what can I do for you
Uh,
guys?
we're just, you said we were group 4 and then said everyone is group 1 except for everyone else. So we're
You
just,
guys are group one. Yeah, group one, two, three, and four. I broke up into 8 groups. So you guys are doing problem one.
so we're doing problem 1, not anything else.
Well, there's 2 problem 1s. There's one
Okay.
problem 1 for friction and one problem 1 for drag. Okay,
All right, thank you.
you bet.
Okay, so do you guys want me to share my screen or do you have it pulled up?
That's always a good way to do it. If somebody's got the ability to share the screen, do it.
I'll do it. Give me a sec.
I'll leave you guys. I can stop sharing that. Put that away. It's so quiet in here.
We're doing the questions separately, and then we're gonna like
Sounds
check
good.
our
Yeah.
answers. Yeah.
I guess the first thing is, do you have a way to figure out what the normal force is, right? You got to do that first. That's my only hint. I'll leave you guys alone. All right.
Okay.
Uh-oh. All right. Something happened. My breakout rooms went away. All right. Well, you're all back. So apparently I hit a button that didn't do what I wanted it to do. So I'm going to try to open all rooms again and send you back.
Were we supposed to come out of the breakout rooms?
No, it was. I have no idea why that is. I don't think I hit the button to end all the rooms, but
I
what happened?
was gonna say, no shot we finished that in 2 minutes.
Yeah, no, you've still got at least another 5, maybe there's 10 more minutes in the class. We'll break it up at the end.
My internet just went out and I had to rejoin the meeting. Can you assign me to the breakout room again?
Who is this?
Emma
Emma?
Mactor.
And
Yeah.
you should be in which group now? Hang on. There
Breakout
you go.
room 3.
You're in 3? Okay.
Yeah.
Put you in 3.
Thank you.
You bet. Nina, how come you're not in your group? Jahil, how come you're not in yours? Let's see. Okay. We're going to go to this one. All right, it's quiet in here.
I have a question.
Good. That's why I'm here. What can I do for you?
So I drew a free body diagram with
Right.
normal force and then gravity.
Okay. Weight. Yep. Yep.
And then I split that into an X component and a Y component.
Good.
And I also have friction.
Okay.
And so I guess it says draw a free body diagram and then find the normal force.
Yeah, I think you have to find the normal force first, because without that, you don't know what the friction force is going to be. So can you kind of in words tell me what the normal force would be?
It would be the Y component of the acceleration.
Of the weight.
Of the weight, yeah.
Yeah. Okay. And so do you have a number for that? I actually don't, but I can put it in my calculator.
It would be the cosine of 27 times gravity.
Yeah. And you don't know the mass, right? That's the problem.
Yeah.
What I would recommend is solve it symbolically, because if I didn't give you the mass, it's going to cancel.
Okay.
If that troubles you, that you want a mass right there, well, if it's going to cancel, you can make it any number in the world. Make it 1 kilogram.
Okay.
All right. That's my my advice. Whenever you don't have the mass, it means it's probably going to cancel. If you just stay with symbols, but if you want to get a number, just make it 1 kilogram. Okay.
Okay. Thank
So
you.
it'd be, that's why I think why you're saying G, because take G and multiply it by some mass, and that'll be actually. That's why I didn't do the calculation until the end. But yeah, cosine of 27 times 9.8 meters per second squared plus whatever the mass is. And the reason it's going to cancel is because you're going to set that equal to ma, right?
Yes.
Once you multiply by the coefficient to get the friction force. And so the two masses will cancel and be on both sides of the equation. All right, I'm moving to another breakout room. All right, what can I do for you guys?
So we're having trouble finding the normal force because we can't find the components of the tension force.
Okay. Yeah, so you can only really do it symbolically initially, right?
Yeah.
Let me put my whiteboard screen up here. And you guys can always use a whiteboard too, I think. And so if I got the free body diagram correctly, there is a normal force, there is a weight force, there is a tension force, and today's topic, there is, of course, a friction force. All right. And so in the Y direction, which with friction you often have to do first, I have two components of that tension, right? I have the X component and the Y component, which I think is what you were asking about, right? All I can tell you about the X component here, what's your angle? Your angle is 34 degrees. All I can tell you is that the tension's X component.
Well, it's equal to the force of friction.
Is it moving at a constant speed? Yep, I agree with you. So, but you still have to get tension times which trig function, sine or cosine here?
Cosine.
Cosine, absolutely. So cosine of 34. And so that must mean that the Y component here is tension times the sine of 34, right? And so the first thing you have to do is figure out what the sum of the forces in the Y direction is. That's normal plus tension's Y component minus weight. And that's got to be equal to 0. And so that tells me that the normal force is the Y component of tension. the tension times, actually the other way around, it'd be minus, if I'm solving for it, times the sine of 34 plus the weight. And so that's as good as you're going to be able to get because you don't know the tension, right? But you know then that the friction force is equal to the coefficient, and this is static friction, right? Now it's kinetic. Yeah, because it's moving, isn't it? Kinetic times the normal force, which is, let's see, the coefficient times everything from right there. And then, as I think you said, that's got to be equal to the tension times the cosine of 34. Okay, but notice there's going to be a tension right in there. So you're going to have to get the tensions together algebraically and then solve for them.
So
Okay.
is it a system of, like, do you have to find
Yeah,
the one variable by subbing in
I think
another
in this
variable?
case, yeah, sort of, because as soon as I push in the tension right here, it becomes minus the tension times the sine of 34 plus the weight. And so what I would, so I've taken two equations right here and I've just got one equation. The only unknown here is tension, right? And so it's just a matter of manipulating. So it's that coefficient times the tension times the sine of 34 with a negative sign. And then I've got plus the coefficient, and this should be subscripted with a K, times the weight is equal to the tension times the cosine of 34. And so you got to get these two terms together and solve for the tension. All right. And that's algebra from there on. So if that's a trouble spot, tomorrow night, Max Tucker and Anna, Anna Hall, they're your folks to help you do algebra. So if doing the algebra, figuring out the tension is trouble, that's the first place. I'll help you as well. All right, looks like I got to jump out of here and end the breakout rooms. Hopefully that gets you what you need.
Okay.
Stop share.
Yes, it does. Thank you.
You bet. All right, looks like everybody's back. And this time I meant to bring everybody back from the breakout rooms because our time's up here. All right. And so for Wednesday, then, finish up either if you're in the first half of the class, the two group one problems, the problem one from the friction and problem one from the drag. The drag problems are admittedly a little bit easier, I hope. One thing that I think both groups came across in their friction problems, and this is often the case, you didn't know something that you wanted. Like in the first problem, you didn't know the mass. In the second problem, you didn't know the tension. You didn't have a number for it. You didn't have numeric values. In those cases, what you have to do is just treat the thing you don't know as a variable, right? It just becomes a variable, and then you've got to manipulate the equations algebraically. That's where the algebra skill comes in. And then you've got to solve for that thing that's missing. Now, in the case of the first problem where you're missing the mass, I would tell you that if you don't know the mass, that means it's going to cancel, right? Because ultimately you're going to have a sum of the forces that's going to have a mass in it, and you're going to set that equal to the mass times the acceleration to solve for the acceleration, and the masses are going to cancel. But if you really want one, because you want to get a numeric value and it's going to cancel, that means it could be any value that you want. Make it 1 kilogram. In the second problem, you're actually solving for that tension. And in order to get the normal force, you're just going to have an algebra expression that might have a bunch of numbers, but you're still going to have tension in it. And so when you put that together with the sum of the forces in the x direction, you'll have tension is the only unknown in an equation, that is the sum of the forces in the x direction being equal to 0. You've got to solve for that tension, even though the tension appears in 2 points in the equation. Now, if that algebra is difficult, I'm more than happy to stay around here. I'll be here for office hours at 9:30 and then again at 10:30. Another resource is the quantitative skills group on Tuesday night, tomorrow night. I think it's 7 o'clock is what Max told me. Max Tucker and Anna Hall, they're great at algebra. Taught them both and they're great students. Questions on that? I think I'm done. I got to let you go because some of you have 9:30 classes. I'm going to go refill my coffee cup and then I'll be back for any questions. You guys have a great day and we'll see you on Wednesday.